Okay, welcome to problem 7.6 out of the textbook. Here we are asked to derive equations for the shear force and bending moment for any location on this beam. Place an origin at point A, and then we want to determine the location and magnitude of the maximum bending moment. And to do that, we're also going to plot the shear force and bending moment diagrams. So the first thing that we want to do is establish our exterior reactions, and to do that what we're going to do is just draw a free body diagram, and the free body diagram will just be the beam with a reaction going at each connection or each point. And then our distributive load, what our distributive load we're going to do is condense it to a point load. And that point load is going to act 1/3 of the distance away from point B. So if this was, here is reaction of B in the Y, and this is reaction of A in the Y. Area of a triangle is 1/2 base times height, right? So in this case it'll be WL over 2, and the distance that it's acting will be 2/3 of L. The distance it will be acting will be 2/3 of L from A, and then 1/3 of L from B. So summing our moments around point A, summing our moments about A with our positive direction going this way. So then we'll have BY multiplied to the length of L minus our WL over 2 multiplied to 2L over 3, and this will equal 0. Solving for BY, get BY equals W sub naught L over 3. Doing the same thing, if we sum our moments about B, which will equal 0, we should get our reaction AY. I'm not going to go through the whole thing, but reaction AY is going to be W sub naught multiplied to L divided by 6. So now that we know our reactions, what we can do is draw another free body diagram. And it says here in the problem statement, it says to place the origin at A. And that's kind of a hint, because if we place our origin at A, and you'll see it'll be a little bit easier, and you'll see why, because if I draw my free body diagram, and with my cut here, and this is my shear, this is my moment, here's my reaction at A, which we already determined to be W sub naught multiplied to L divided by 6, and then we'll have a distributive load, right? That's going to be here, but this distributive load, as we determined earlier, it's W sub naught, right, at its maximum value when it reaches point B. But since we're making an arbitrary cut somewhere in the member, this distributive load, we have a distance of x, right? This distributive load then isn't going to be the full magnitude W sub naught. What this loading, the magnitude here, is going to be W sub naught multiplied to x divided by L. And where we get this from is just because it's a linear equation, right? If you just think about the slope of a line, if we think y equals mx plus b, where if we start at A, our value would be 0, so B goes to 0, right? And what would the slope of our line be? Our slope of the line, m, right, is going to equal the maximum magnitude, which would be w sub naught, then divided by our length, which is going to be L, and then x is just x. So the slope of the line, or the equation then, is going to be w sub naught x divided by L. Okay? So using this, what we can do is find our shear, right? So summing the forces in the y direction, sum the forces in the y equals 0, positive moving up, right? And so what we can do is, what we'll see here is we'll have a sub y, which is w sub naught L divided by 6, minus our distributive load, magnitude, which is going to be w sub naught multiplied to x divided by L, and then the distance, right, where it's going to act from, it's going to be 1/2 of x, right? So x over 2. And this will then be minus shear equals 0. And so what we can do now is solve this for our shear. And so our shear, we should get a value that says w sub naught L divided by 6 minus w sub naught x squared divided by 2L. And this will be the shear equation for our member. And if you think about this, if you just think about our rules of calculus, if we started with a linear function, right, y equals mx plus b over here, I drew this function. If you were to integrate this function, right, with a constant being w sub naught L over 6, then if you integrate this, you should get wx squared over 2L. So thinking about that again, if you integrate the shear equation, then you should get our moment equation, right? It's just our calculus, basic calculus there. So, but what we'll do is we'll sum the moments about our shear cut in this one. So we'll sum our moments about V, which equals 0. Then this will be negative a sub y multiplied to the distance of x plus w sub naught x over L, which is our force, multiplied to x over 2, because this is the area of a triangle, right? So our force, which is our height, base times height, divided by 2, which is 1/2, and then multiplied to our moment arm, which is going to be x over 3. So if we're summing our moments about the shear point, it's 1/3 the distance. This is our moment arm here, 1/3 the distance, and this here is the area, area of a triangle, okay? And then we're going to add that because we have a positive direction for a moment, add that to the moment, and that equals 0. So you should get a moment at B, which should equal negative w sub naught x cubed over 6L plus w sub naught L 6 multiplied to x divided by 6. Okay? And this is the equation for our moment on this member. Okay? So the next thing that I want to do is it'll make it easier to solve part B, this equation. So part B, it says determine the location and magnitude of the maximum bending moment. Okay? So determine the maximum location in magnitudes. What I want to do is just draw our shear force and bending moment diagrams. Okay? So to do that, the first thing I'll do is just go ahead and draw a line. And this is our member, right? So this is A and this is B. Okay? So with our shear, when x is 0, we'll have a shear force value, right? So if I draw, So if I draw our shear underneath this, and call this our shear, the magnitude at the very beginning is going to be W sub naught multiplied to L divided by 6, okay? And so if I plug in, if I want to know where this is equal to 0, right? Can set it equal to 0, solve for our x value, right? Set it equal to 0, solve for x, and you'll get an x, which should be, at some point, this will be a parabolic function, right? Because it's a parabolic and it's a negative parabolic function. So it curves down to this point, right? And if you do the math, this distance should be 5,77350 multiplied to L. Okay? And then from there, the shear will become linear, right? And then once it gets here, it's a negative W sub naught multiplied to L divided by 3. And it goes straight up back to 0 here. Okay? And so where our function crosses the axis, x-axis of 0, this is going to be the maximum magnitude. This is going to be the location of the maximum magnitude for our moment, right? So I'll draw another line. This is our moment equation, okay? And this, our moment, it's a negative cubic function, right? And when x is 0, our moment is 0, okay? And also when our x equals L, it should also be 0. So we're going to start and end on this horizontal axis, okay? And the maximum value should be right where we cross 0 for our shear, okay? So our value here, plugging it in, solving this using your tools from calculus again, right? I think it's called the second derivative test. You can get a cubic function. I know this is kind of hard to draw here, a little bit crooked, but that should be a cubic function, and then it will arc back down this direction. And the magnitude here, the magnitude is going to be 0.06 4150 W sub naught L squared. Okay, and that's our moment. So what we'll do for part B of this problem is we wanted to determine the location and magnitude of the maximum bending moment, right? So let's go back up and read our, determine the location and magnitude of the maximum bending moment. So the location and magnitude, well, our location here, right, we determined already, right, is going to be found by saying our shear, right, is W sub naught L over 6 minus W sub naught x squared over 2L, which equals 0. And I mentioned it before, what you do is you take this function, you set it equal to 0, and you solve for x, right? So W sub naught x squared over 2L equals W sub naught multiplied to L divided by 6. Solving this, you should get x equals the square root of L squared divided by 3, and x should therefore equal 0.577350 L. Okay, so that's the location of maximum value, right? Now, the actual magnitude, right? The magnitude, well, how do we determine that? Well, okay, with the same thing we did for shear to find the location, we're going to do the same thing for our moment equation. You're going to take that, set it equals 0, and solve for or I'm sorry, I take it back. We're going to take this x value and plug it into our moment equation and solve for our moment, right? So then our moment is going to equal, negative W sub naught x cubed divided by 6L plus W sub naught L multiplied to x divided by 6, where x equals 0.577350 L. Okay? So plugging this value in to our x values here, right? And I'm not going to go through the algebra, but the value that you should end up with is 0.064150 W sub naught L squared. And that will be the magnitude of this bending moment. Oops. And that will be the magnitude of the bending moment. And this is the answer. And then you get a check mark.